Hi, this is Dr. Remenacker. In this particular video, we're going to continue looking at graphing using the first derivative. In the video just prior to this one, we did several functions where we computed the derivative, set it equal to 0, and then using that derivative equal to 0, identified critical values being locations where you have a potential relative maximum or relative minimum, and then sketched out some graphs. In this particular video, I want to continue looking at how do you sketch out graphs, how do you compute relative maxes and mins, and I want to more carefully define something that we were using in the last video that's actually referred to as the first derivative test. I didn't put a specific name to it in that video because I just want you to get used to the idea of what's going on without formalizing it first. The first derivative test essentially says if you have a continuous function, okay, and it needs to be a continuous function on an open interval around some point that we're interested in, okay, then it has a critical value if one of the following happens. The first thing that can happen is if we're on some interval from A to B, so let's say I'll draw this in the upper right-hand corner. Let's say we've got some number here A, we have some number here B, and at C, okay, at C, the derivative is equal to 0, so this is a critical value. Okay, so C is our critical value. If we evaluate the derivative on this side, okay, and it's greater than 0, and then we evaluate the derivative on the right side using some value on the interval from C to B, and it's less than 0, what this means is that it's first increasing, the slope's positive, then it's decreasing, the slope is negative, which means that we have what is referred to as a relative maximum. Okay, it's a high point because the graph goes from increasing to decreasing. So you can see here we have a high point on the graph. The second portion of the first derivative test is going to focus on situations that are just the opposite. What this says is if we have this same interval from A to B, and there's some value C where the derivative is 0, so it's a potential critical value, and to the left of C, the derivative is negative, to the right of C, the derivative is positive, we're going from decreasing to increasing, which means our graph is essentially doing something decreasing, increasing, making this point where x equals C a minimum. Now we're going to refer to these as a relative maximum and a relative minimum for right now. In a later video, we're going to get to something called an absolute maximum and absolute minimum. The idea of a relative maximum and a relative minimum is you can have a function that goes like this. This leftmost point is a maximum, but it's not the biggest maximum. You can see to the right of it, there's a, if you would, a taller mountain. So relative to things around it, this is a relative maximum. Using the same reasoning, this next location here is a minimum, but it's not the lowest minimum. You can see on the graph where there's one even lower. So this is referred to as a relative minimum. Relative meaning compared to everything around it, it's lower than anything else. Okay, so we are going to refer to each of our critical values as a relative maximum or a relative minimum if they meet one of these two criteria until we move a little bit further to determine where is the absolute highest point, if there is one, and where is the absolute lowest point, if there is one. Those will be called absolute maximums or absolute minimums. Okay, so that gives us an idea of a relative maximum and a relative minimum. There's a third possibility here. And then moving back up to this little number line in the upper right corner, you can have a situation where one of two things happens. First situation, the derivative is positive on both sides of the critical value. That means it's increasing, levels out, and then increasing. Both slopes are positive, so it's going up. In this case, this is not a relative maximum or a relative minimum. It is neither. Okay, so if both of these derivatives can be positive, they can also wind up both being negative, which means it's decreasing, levels out, and continues decreasing. And using the same reasoning as with a situation where they're both increasing, we don't have a relative maximum or a relative minimum here. Okay, it's just a point where things level out and then continue on a downward trend. So as we go through each function that we're going to practice locating critical values on and then graphing, we're going to need to keep in mind that we're always going to use this first derivative test. And there are three possibilities. It could be a relative maximum, it could be a relative minimum, or it could be neither a maximum nor a minimum. It could just be a location where it levels out. Okay, so with this first derivative test in mind, and we'll come back to this as we move through this example, you're given this function 4x squared e to the negative x, and you're asked to compute the critical value or values and to sketch a graph. Well, as will always be the case, the first thing we're going to do here is we're going to compute the derivative. This same problem could be stated as, given the function 4x squared e to the negative x, compute the maximum or compute the minimum, which is really what's going to wind up happening as you move into applications in the real world. They're not so much so going to be thinking about critical values, managers or whomever. They're going to be concerned about what's the maximum, what's the minimum. And they're going to use those words, maximum or minimum or optimized or something to that effect. And what they really are saying is compute the critical values, use the first derivative test to determine if it's a max, min, or neither. And then as we move on into further sections in the book, determine if it's an absolute or a relative max, min. So there's a whole lot wrapped up mathematically in what seems to be initially a fairly simple request. Just find words, maximum. Okay, so if we're going to locate critical values, the first thing we need to do is to compute the derivative. We'll notice in this problem, we have here this factor 4x squared times e to the negative x, which I'm sure you realize by now, you know that that means that this is going to be a product rule, which is going to be f prime g plus f g prime. I'm hoping that everybody's pretty well got that memorized by now, and if you don't, I'm just going to use it probably one or two more times. Okay, f prime is going to be 8x, f prime being the derivative of the 4x squared. G is just this e to the negative x, copying down the second factor. Then we're going to do plus. Remember, you only use the minus with the quotient rule. Then it says f, well, that's going to be a 4x squared. G prime. Okay, now for G prime, this is actually going to be a chain rule. You take the derivative of the outside function, e. Well, the derivative of e is just going to be whatever you started with. That's going to give us back our e to the negative x. And then, according to the chain rule, after you've done the derivative of the outside, you now do the derivative of the inside. The derivative of negative x is going to be a negative 1. So this can clean up a little bit and can be written as 8x e to the negative x minus 4x squared e to the negative x. So there's our derivative. What used to be the whole problem, like compute the product rule, is now just the start of the problem. Remember, when you have a maximum or a minimum location on a graph, okay, so if you have something like this, or something like that, the slope of the tangent line will always be 0. Well, if the tangent line is 0, that means we need to take our derivative, which is this right here, and set it equal to 0. So essentially, step 1 is compute the derivative. Step 2 is going to be to take that derivative, set it equal to 0. So we have this 8x e to the negative x minus 4x squared e to the negative x. And we're going to set that equal to 0 and solve that. Yeah, that looks like fun. Well, notice that both terms have an e to the negative x in them. And they both have a 4 in them. And I'm going to leave the, well, I'm going to leave the x there for right now. So I'm going to factor out a 4 e to the negative x, which is going to leave me then with 2x minus x squared equals 0. Okay, so we have that. Okay, so all I did was I factored out a 4 and an e to the negative x. Now, I can do a little more factoring here. I can rewrite this. I still have my 4e to the negative x. Then I can factor out an x, leaving us with 2 minus x equals 0. Okay, so we've got this to the point now where we're ready to do some algebra and solve this. There are 3 situations here that we want to consider. Remember, if you've got 3 things multiplied together and it equals 0, that means that at least one of them has to be 0. So that means our 4 e to the negative x equals 0. The second situation is actually a pretty easy one to solve. X equals 0. Or our third factor, 2 minus x equals 0. Well, let's go after the third one here. That's pretty straightforward. This says that x equals 2. So we have 2 possible critical values here. We have one at x equals 0. We have one at x equals 2. Now let's go back to this 4e to the negative x. We could divide both sides by 4. And that's going to give us e to the negative x equals 0. Okay. Up to this point, when we have a function with e in it, the way we've dealt with that is to apply natural log to both sides. Well, you can go ahead and try that. And if you apply natural log to both sides, you get negative x equals the natural log of 0. Plug natural log of 0 into your calculator and see what you get. Yeah, it didn't work so well, did it? What winds up being the case is e to the x and e to the negative x never equal 0. If you'll think back to the graph of e to the x, the graph of e to the x goes like this, where it runs asymptotic to the x-axis, but it never intersects the x-axis, so you never get a y value of 0. E to the negative x goes like this, and the same deal. You never get a y value of 0. So what winds up being the case here is this first of our 3 factors, the 4e to the negative x, is never 0. That leaves us, though, with 2 critical values. Okay, our potential critical values I'm going to abbreviate critical values as CV, are going to be at x equals 0 and x equals 2. Okay, so we have those 2. Now, we're going to need to do the first derivative test on each of these potential critical values. I'm going to work on them one at a time, so it's a little bit easier to keep track of what's going on. First, let's take a look at x equals 0. Okay, so what I'm going to do here is sketch out a graph. Here's the value I'm interested in, x equals 0. What I'm then going to do is I'm going to come back up here and for my derivative right here, I'm going to evaluate the derivative f prime at something to the left of 0, then evaluate the derivative f prime at something to the right of 0. As with the earlier problems, I'm going to make my life a little bit easier here by pulling my calculator up. And notice I already have entered into y1, the original function, 4x squared e to the negative x, and in y2, 8x e to the negative x minus 4x squared e to the negative x. And as always, to make it easy for me, I always put the function in for y1, the derivative in for y2. So I know what function I'm dealing with at any point in time. Okay, so I have my functions in. Now I'm going to go to the table. And oh dear, there's a bunch of stuff here. So I'm going to go ahead and delete all this because that's from a previous problem. What I want to be able to do, moving back over to the left-hand side here, is I want to choose some x value to the left of 0, then choose an x value to the right of 0. There's no extra credit for picking something particularly hard, so I'll just go with -1 and +1. Having chosen those two values, I'm just going to go ahead and enter -1 in, and then I'm going to enter 1 in. And at this point, I'm not really concerned about the x value, or I'm sorry, the y value. Okay, so I'm not going to pay attention to y1. What I'm concerned about is the slope, which is y2. When x is a -1, notice the slope is negative. When x is a +1, notice the slope is positive. That's all I need to know. So I'm going to come over here and I'm going to put down it's negative, it's positive, so it's decreasing, it's increasing. Using the first derivative test, if I go from decreasing to increasing, okay, that's option number 2 here. When I go from decreasing to increasing, tells me I have a minimum there. Okay, so at this point, I have a minimum. The critical value is x equal 0. I know it's a critical value because it's a minimum. Okay, x equals 0. The critical point is going to be x equal to 0. Now, I can come back to the calculator, and I don't want the y value at 1. I don't want the y value at -1. I want the y value at 0. And when I substitute in the y value at 0, or the x value at 0, the y value is also 0. And notice the slope there is 0. That's good news. I want to be at a location where the slope is 0. Well, the derivative is 0, so the slope is 0. Okay, so one of my critical points, which is going to be a minimum, is right there. Then I'm going to come back and I'm going to do the exact same series of steps, but this time I'm going to see what's going on at x equals 2. So the first thing I'm going to do is to put down 2. Then I'm going to evaluate the derivative to the left of 2 and go evaluate the derivative to the right of 2. To the left of 2, well, we could do something like 1. And notice, hey, I've already done that. It's positive. So I can just go ahead and put down that's greater than 0. Something to the right of 2 would be something like, let's say 3. Okay, then what I'm going to do is I'm going to go back to my calculator, and remember this time I want to use the x value 3, so I'm just going to put in 3, and I'm looking at the derivative, which is a negative value. Okay, so this is going to give me then, if the derivative is negative, less than 0, on that interval it's going to be decreasing. Whereas on this interval between, to the left of 2 actually, it's going to be increasing. If you go from increasing to decreasing, we can go back up and reference our first derivative test information. If it goes from increasing to decreasing, that gives us a maximum. Okay, so on this second one, we can put down the critical value. We do have one at x equals 2. The critical point is going to be x is 2, and I need to get the y value. So it's back to the calculator, and I'm going to use an x value of 2 this time. So it's going to plug in 2, and my y value is going to be let's say 165. Keep it to 3 digits or 3 decimals. Okay, so 2.165. Now, with this information, I know that I have here a maximum at 2, a minimum at 0, and I can go use this data and take a shot at sketching out a graph. All right, so what's this graph going to look like? Well, it's going to have the point 0, 0 on it. Remember, that's this location right here. It's also going to have the location come over 2 and up a little more than 2. It's going to have something going on here as well. You're going to want to label these. This is 2, 2.165. And this other location here is 0, 0. Always locate your points. By locate, I mean label them. It's really difficult. If you were just looking at this graph, I doubt that you could confidently say that for this point, the y value is 2.165. I just don't think you could read that off of the graph, and I suspect you'll agree with that. Now, what we need to do next is we need to take the information that's at the very top of the screen. Okay, to the left of 0, it's decreasing. On this interval between 0 and 2, it's increasing. To the right of 2, it is decreasing. Okay, so with that information, we can come through here, decreasing, increasing, and then decreasing. Now with this, we got to be really careful. Okay, we want to keep in mind that we're working with a function with e to the x in it. And we already have the location where it goes to 0 because of x being 0 accounted for. What this is telling us is that this graph is never going to hit 0 again. It's going to run asymptotic to the x-axis like that. And here's a graph of your function, f of x equals 4x squared e to the negative x. Your graph doesn't have to be absolutely perfect. Your graph does need to look similar to what you would expect the graph to look like. And your graph must have your critical points labeled. Okay, so be sure that when you're working on these, you get into practice of always labeling your critical points, because there's no way you can read these numbers by just looking at the graph. Okay, you can't confidently say, well, the y value is 2.165, and you really can't confidently say the x value is 2. The way I've got that graph, it looks like it might be 1.8 or 1.9, but that's the catch with graphs. They're not perfect. Okay. Okay, so there's that one done. Let's take a look at another one. For this one, let's take a look at something like, let's call this h of x equals let's say x minus 4 to the, let's say, how about to the 3/4 power plus 2. That looks like fun. Okay. The first thing to realize here is we do have a, tell you what, let's change, no, let's leave this a 4. We do have a root, and on this root, we cannot have negative values, okay, because a fourth root is not defined, just like a square root is not defined for negative values. So our domain, oh man, we gotta watch our domain here. Our domain is going to be any x value. Okay, so this x minus 4 has to be greater than or equal to 0, which means x has to be greater than or equal to 4. So our domain is going to be from 4 to infinity. Does that make sense? Okay, so we got to watch our domains. That's why we did that stuff back in our reviews section. Yep. Okay, now we're going to step through just as we did in the previous example. First thing we're going to do, compute the derivative. So we have h prime of x. This is going to be a chain rule because you have an outside function, e to the 3/4, applied to an inside function, x minus 4. So our derivative is going to be 3/4. Just going to copy the inside down. Subtract 1 from the exponent. It's going to be a negative 1/4. Now be careful because we now, using the chain rule, need to do the derivative of the inside. In this case, it's just 1. On a quiz, test, or whatever, I would very likely be inclined to put something like a 7 in front here just to make sure that you really are doing the chain rule correctly. If there's a 7 there, there would then be a 7 down here as well. So be aware of that. Don't just assume that you're going to have a 1 there. Okay, that won't play out so well for you in the long run. Then we have plus, and the derivative of 2 is 0. All right, so now we have this. Okay, we need to figure out where this equals 0. So step 1 is compute the derivative. Step 2 is to take our derivative, 3/4 times x minus 4 to the negative 1/4, which can be written as 3/4 times the 4th root of x minus 4 and set that equal to 0. There's a problem here. The only time a fraction will ever equal 0 is if the numerator is 0. Well, the question is, when does 3 equal 0? Say, what? 3 never equals 0. So this function is never equal to 0. If you'll think back, in the previous video, we talked about critical values or critical points occurring at 2 situations. One of those situations is where the derivative equals 0. The second situation is where the derivative is undefined. Well, this doesn't happen. This first situation doesn't happen with this problem. However, this derivative is undefined when x equals 4. If you plug 4 in there, you get a 0 in the denominator. And a 0 in the denominator is always a problem. So we have a critical value at x equals 4. Okay, we know it's a critical value because it's undefined there. Okay, we need to compute then a critical point. This critical point is not going to be too hard to compute. If we bring the x value up to our original function, there we are, and we substitute in 4 for x, we're going to have 4 minus 4 is 0, and any root's going to be 0. Then we have plus 2. You could do this one back in first grade. 0 plus 2 is 2. All right, so that has that. Now, what we want to also do here is we need to figure out, is the function increasing or decreasing? Okay, so just as we've done previously, we're going to set things up here. I'm going to do 4 because my critical value is there. Then I'm going to evaluate the derivative at something to the right of 4. Oh, let's say something like 5. Now, you really don't need the calculator for this one because all we need to know is this thing positive or negative? Well, if I take 5 and I put it in here and I'm looking at my fraction, the numerator is going to be positive because 3 is positive. The denominator is going to be 4 times the fourth root of 1. Well, that's positive as well. So we have a positive over a positive. Our slope is positive there. Great. So how do we go about graphing this thing? Well, to graph this, I know I have something going on at 4, and the location is over 4 and up 2. So I'm going to go 1, 2, 3, 4, and up 2. And at 4, 2, I'm going to put a point, and I'm going to label that as 4, 2. Now, the question might be here, do I use a solid or a hollow dot at 4, 2? Well, let's go back up to our domain, which is in the upper right-hand corner, and notice the domain says we're allowed to include 4. So that means a solid point there. Okay, so we have this. Now, we know that there's nothing over here to the left of 4 because this is not in the domain. To the right of 4, our graph could increase like this, or it could increase like this. Well, which is it? Well, the way the green line is drawn now, that's an exponential function. That's the way something like e to the x would behave. This is a root. Remember, it's a fourth root. Okay, well, let's think about what the square root graph like. Square root graphs like that. So guess what fourth root also graphs to look like? Kind of the same thing. So we wind up with something like that as our graph. Notice here on this whole side, there is nothing. Absolutely nothing. And the reason is it's not in the domain. Okay, so this gives you 2 more problems to work on. This should be a good start point for you. At this time, you should be in good shape to start tackling the homework.